Okay, in our previous example, it was a pretty simple one, just the shortest distance between 2 points is a straight line. What I want to focus on today is something a little bit more complicated. We're going to talk about extremizing a surface of revolution. So let me define what we want to try to solve here. So suppose that we have a curve between 2 points, and we'll call those points little a, and little b, big B. Okay? So we have a curve between these points, so let me draw that. That curve is obviously defined by u of x. Okay? So here's our x-axis. Here's u of x. And let's say that this is the location A. And how about this being the location of B. And we have some curve that connects them. Okay? So as before, if we wanted to talk about what's ds, right, we could write this. This would be du, this is dx, and then this length here would be ds. Okay? And then this, of course, is just the curve u of x. So what we want to do is we want to take this curve and we want to revolve it around the x-axis. So you can kind of see if we did that, it would make something that looks like a cooling tower for a nuclear power plant laying on its side or something like that, right? And if we had a straight line, it'd look something like a revolved. It would just look like a cone of sorts, right, without the tip. So what we want to do is we want to find u of x such that the surface of revolution about the x-axis is a minimum. Okay, so that's our goal. Okay, so you can see what we want to do here is we want to create a functional and then extremize that functional by finding the appropriate function u of x. Okay, so here's our solution. We're going to denote S, capital S, as the surface area. So if we want to think about what would ds, as some increment in that, it would be basically a band revolved around the x-axis. So it would be essentially whatever this distance here u is, right? That acts as your radius. So it would be 2 pi u times ds. That would be our d little s. That would be our d big S. Okay? So if we denote S as the surface area, then we can write the following, that d big S is equal to 2 pi times u times ds, right? Where ds is given above. Let's call that equation 1. So what we want to do is then recall from our previous example, we know what ds is, right? We have that ds is equal to the quantity 1 plus u prime, the quantity squared, to the 1/2 times dx, right? Call that equation 2. And so then we can write the surface area S, which we'll say is a function of u, is going to be equal to the integral from a to b of ds, which, looking at equation 1, we can write the integral from a to b of 2 pi u, and I'll remind you that's a function of x, times ds, and then substituting in 2 here, we have the integral, and I can pull out the 2 pi, right? So I have the integral from a to b of the quantity u now times ds, which is going to be 1 plus u prime quantity squared to the 1/2 dx, and we'll call that equation 3. So we look at equation 3 and we make the observation that it's in the form of a functional like we've defined before. And that form, remember, was I of u is equal to the integral from a to b of some of integrand f as a function of x, u, and u prime dx, right? So we observe that this is the right form, right? And so we know what the Euler-Lagrange function is. In this case, we know that we can compare equation 3 to this form and see that f is really a function of only u and u prime, right? And this turns out to be u times the quantity 1 plus u prime, the quantity squared, to the 1/2, right? That's what f is equal to. Call that equation 4. And now let's recall the Euler-Lagrange equation that we already had developed for that type of functional. Right? It was d by dx of the partial of f with respect to u prime minus the partial of f with respect to u is equal to 0, right? Call that equation 5. Now, I can substitute equation 4 into equation 5 to get the following. We have then d by dx of, so in this case we have the partial of f with respect to u prime, so I have then u times 1/2 times 1 plus u prime, the quantity squared, now to the negative 1/2, this is just using the chain rule, remember, times the derivative of what's inside, so that is going to look like times 2 u prime, right? So that's the first term, and then minus partial of f with respect to u, that just becomes the quantity 1 minus u prime, the quantity squared, to the 1/2 equals 0. Okay, let's do a little bit of simplification. My 2 times the 1/2 cancels those out, and so I'm left with, in a little bit of a simplified form, d by dx, u times u prime is the numerator, and the denominator looks like 1 plus u prime, the quantity squared, to the 1/2, right? And then minus a 1, oops, I should have made this a plus, 1 plus u prime, the quantity squared, to the 1/2 equals 0. Let's call that equation 6. Okay? Okay, so one thing that I guess I'll just mention up front is that these aren't always going to be so clean, right? So this is an example of a little bit more of an algebraically complex, I guess, problem that requires a little bit of work to kind of simplify out. So you can look at this, and we know how to take the derivative with respect to x of that quantity, right? Even though it's going to be messy, right? We can use the quotient rule here. So let's do that. So we're going to expand the derivative term in equation 6. So if we do that, right, remember that this is u over v, then the quotient rule says that the derivative is v du minus u dv divided by v squared. So let's do v du first. So v is just 1 plus u prime, the quantity squared, to the 1/2. There's v. And then du, that quantity, we need to use our product rule here. So this is going to look like u times u double prime plus u prime, the quantity squared. Okay, so that's the first term. The second term, it's v du. Now we need u dv. So u is u times u prime. And then dv looks like 1/2 times the quantity 1 plus u prime, the quantity squared, now to the negative 1/2, right? Times the derivative of what's inside, 2 times u prime. Okay, there's something that's a little tricky here. In the first, just before this, I said I ended with this, right? But this is the derivative with respect to x. And so I still have to now take the derivative of u prime with respect to x, which is u double prime, right? So it's kind of maybe make that double prime a little bit more explicit. Double prime, okay? So just don't forget that. And then all of that is going to be over 1 plus u prime, the quantity squared, to the 1/2 squared, right? So just that's it, right? That's our denominator. And then over here, we're going to still have our minus 1 plus u prime, the quantity squared, to the 1/2 equals 0. Okay, let's call that equation 7. So now obviously if this is a a problem that maybe on like a timed exam you'd be thinking something is going horribly wrong. This looks too messy, but it's not an exam, and we can do a little bit to clean this up. So let's first try this. Work about simplifying this. Okay, so simplifying equation 7. Let's just first look at this first term. If I divide top and bottom by this 1 plus u prime squared to the 1/2, then I'm left with u times u double prime plus u prime, the quantity squared, divided by 1 plus u prime, the quantity squared, to the 1/2. Okay. Now let's go ahead and look over here. I have a minus. My 2 and my 1/2 will cancel out, right? And so I end up with, let's see, that first term is a u, and then I have a u prime and a u prime, so this becomes then u prime, the quantity squared, and then I have a u double prime, right? And then in this case I have 1 plus u prime, the quantity squared, to the 1 power, and then this is to the negative 1/2. So if I multiply top and bottom by 1 plus u prime squared to the 1/2 power, I can get rid of this. But then this denominator now becomes 1 plus u prime, the quantity squared. Now this is to the 3/2, right? Hopefully this is all, not too terrifying. It's just basic algebra. Okay, and then we have this term 1 minus 1 plus u prime, the quantity squared, to the 1/2 equals 0. Okay, so let's call that equation 8. So we're working on simplifying this. So if you're looking at this, it looks to me like I could clean up a lot if I were to multiply the entire equation by this denominator. Okay, so we're going to try that. So multiplying equation 8 by the quantity 1 plus u prime squared to the 1/2 gives the following. So now I just left with the numerator here, u times u double prime plus u prime, the quantity squared, right? And then this is going to be minus u times u prime, the quantity squared, times u double prime, divided by 1 plus u prime, the quantity squared, right? And then this is going to become minus 1 plus u prime, quantity squared, equals 0, let's say. Okay? Okay, and what we can see from here is that I have a positive u prime, the quantity squared here, and then if I distribute this negative out, I have a negative u prime, the quantity squared there, so that this term and this term cancel out, and I'm left with u double prime minus u times u prime, the quantity squared, times u double prime, divided by 1 plus u prime, the quantity squared, minus 1 equals 0. Let's call that equation 9. Okay, so what do we do next? Well, if you look at this again, what if I multiply everything in equation 9 by the quantity 1 plus u prime squared? Okay, so let's try that. Okay, when we do that, this becomes u times u double prime times the quantity 1 plus u prime squared, and then we lose the denominator on this term. This becomes u prime, the quantity squared, times u double prime minus this quantity 1 plus u prime squared equals 0. Well, let's look at this. So this second term is going to be u double prime, u prime squared, minus u double prime, u prime squared. These cancel out. And so all I'm left with here is u times u double prime. And then if I come over here, then I have a minus u prime, the quantity squared, minus 1 equals 0, right? So I've significantly simplified it now. Let's call that equation 10. Okay, so now how do we solve something like this? What I'm going to do next is tool that we can use that you may be a little unfamiliar with. So I'm going to use the chain rule kind of in reverse. Okay, so let's say I'll use the chain rule to define. I'm going to say the u double prime we know is equal to du prime dx, right? That's a given. But what, and usually we just leave it at this, but what if I said, well, maybe I want to use a chain rule and call this du prime du times du dx, right? That's a valid use of the chain rule. So this quantity obviously is u prime, and then I'm left with u prime times du prime du, okay? Why did I do that? Well, I did that so that I will be able to solve this via separation of variables. So I'm going to substitute equation 11 into 10. And when I do that, that u double prime term becomes, so there's the first u. Now I have u prime times du prime du, right? And then still minus u prime, the quantity squared, minus 1 equals 0. So that's my new set of equations. Okay, now what I want to do is separate variables. So when I do that, I'm going to move the u prime squared minus 1 to the other side, and then divide by u prime du prime, and I'm going to keep the u over du on the other side. So I have u over du on this side, and on the other side, I have u prime, the quantity squared, minus 1, divided by u prime times du prime, right? Of course, this isn't yet helpful. What do I want to do? I want to invert both sides. So I'll just say here, this is inverting. And this then becomes du over u is equal to u prime du prime divided by u prime, the quantity squared, minus 1. Let's call that equation 13. And now I can just integrate both sides. So I can integrate equation 13. So obviously du over u, if I integrate that, just becomes natural log of u. You'll notice I've done a few things maybe a little sloppy. I didn't put the magnitude of u, I just put u, okay? And so I'm going to come back and make some comments about the solution that we come up with here. But this will be the natural log of u plus some constant, we'll call it c. And then I can go ahead and integrate the other side. You can either integrate that directly or just look it up in tables. This becomes 1/2 times the natural log of 1 plus u prime, the quantity squared. Okay? No wonder I was confused. This should be a plus, right? Because I moved both of those to the other side. Okay, so that makes more sense. Okay, so this is where we're now left with, and so what we're trying to find, obviously we're trying to solve for u, right? So how do we do that? Well, let's think about what we can do here. If this is just an arbitrary constant, then I could make it also log c, since that's also just an arbitrary constant, right? And if I make that into an arbitrary constant, so I can also I can change the sign on this at will. So I'm going to say that's a minus, right? And so then this is going to become natural log of u over c. I'm going to go ahead and multiply the 2 out and have this be 2. And that's going to be then equal to a natural log of 1 plus u prime, the quantity squared, right? Remember, going back to your log rules, if I have a coefficient out front, this can be written then as natural log of u over c, the quantity squared, is equal to the natural log of 1 plus u prime, the quantity squared, right? Let's go ahead and call that equation 14. And now what I'm going to do is take each of these and raise them as exponents of e, right? So taking equation 14 as exponents of e, right? Now I can just write then that that's u over c, the quantity squared, is going to be equal to 1 plus u prime squared, right? So we're getting, again, simplified a little bit. Now let's solve for u prime. Gives u prime is going to be equal to, this quantity u squared over c squared, right, minus 1 to the 1/2, which we could say is equal to u squared minus c squared, that quantity to the 1/2 divided by c. Let's call that equation 16. Okay, what do we want to do now? Well, let's try to separate variables. So u prime we know is du dx, and that's going to be equal to u squared minus c squared to the 1/2 divided by c, right? So if I do my separation of variables, I end up with du over u squared minus c squared to the 1/2, right? And that's going to be equal to dx over c. Let's call that equation 17. Okay, now I can integrate equation 17. Okay, and again, you can either do the integration yourself or you can look it up in a table and see that the integral here gives you the inverse hyperbolic cosine of u over c. And that's going to be equal to, on this side, that's going to be equal to x over c. And then we don't have limits of integration, so we have to have a constant. Let's call that plus d. Okay, we'll call that equation 18. So we're just about done. Let's solve equation 18 for u. And obviously we do that by taking the actual hyperbolic cosine, right? And so we end up with that u over c is equal to cosh of x over c plus d. And finally, multiplying by c, we have u of x is equal to c times hyperbolic cosine of x over c plus d. Okay? There is your extremizing function. Might not have been what you expected. Let's call this equation 19. What do we do? How do we know the coefficients c and d? Well, we'd have to go back in and actually choose values for a and b, okay? So let me just mention that. You're going to solve for the coefficients c and d using the endpoints a, capital A, and b, capital B, right? Let me give you some remarks about this solution. Number 1. Equation 19 is what is known as a catenary, or sometimes it is called the catenary curve. Okay, and it occurs often in nature. For example, any hanging flexible object, such as a power line or a suspension bridge, okay, any of those are going to hang in this shape that's called a catenary. So if you've been driving down the interstate and looked at the power lines and you see them hanging, probably in your mind you're thinking, well, if I were to estimate that, I would say it's a parabola. But in fact, it actually is a catenary. And so this just gives you one example of how that comes about, how we know that. We know that because we are minimizing a function L, and in the course of doing that, we're extremizing by selecting a function that gives us that minimum. Okay, something to be aware of. If you remember, I did a little bit of sleight of hand. I didn't put absolute values on. I made some other assumptions as we were moving through here. When I multiplied and divided through, I assumed that, let's say, that those values weren't 0. Those kinds of things. So equation 19 is an absolute minimum only for a certain set of conditions with AA and BB. It can also provide a relative minimum for other endpoint conditions. And for certain conditions, it cannot actually be a solution at all. Okay, so we're not going to go into the depth that would be required to break down when it would and wouldn't be appropriate. Mostly, I just wanted to show you how we can arrive at something that's pretty common for you to have seen your whole lives and probably didn't know the kind of shape that it was. We could have done this by minimizing energy of a hanging chain, and we would have come up with the same kind of solution. Okay? One final comment is that if we wanted to get a local minimum for every case, we would need to use what's called the Goldschmidt discontinuous solution. Okay, but that's going to be beyond the scope of what we're going to cover in this course. So anyway, this is just one more example of how we can use the Euler-Lagrange equations to come up with the function that extremizes a function L. One other thing just to keep in the back of your mind is that we are, as we've given the problem now, we are developing a function, right? And when we come up with a function, the functions that we are typically working on are going to be one-to-one functions, right? So if the problem requires something besides a one-to-one function, we're probably going to need a different or a modified approach to come after that. So we'll talk about that later in the class, but I just wanted to point that out, that obviously you could plot this hyperbolic cosine function and see what it looks like, and you'll see that it's a one-to-one. It's not a circle or something like that. But sometimes if a circle is the correct solution, then we would need a method to compute that. And so we'll talk later about how we go about formulating those classes of problems.